Thank you for coming back once again. In this video, we are going to be talking about substitution, substitution methods in integration. And first I'm going to start off by defining what substitution is and what we can do to use it, how we can compare it to differential calculus. So we're going to first define a couple of terms where u is defined as f of x and du is the derivative. It is the differential of the term. So it's the derivative of f of x times the differential d of x. And if we think about it for a second, we know that we can do this because if u is f of x, du dx is equal to f prime of x. So we're able to just carry over the d of x. And using these as our definitions, we can define that the integral of u to the n power du is u to the n plus 1 over n plus 1 plus c. And this is one of our many equations that we can use in substitution. And we can use any formula for integration. We could use any of the equations that we've learned so far, and instead of using x, we can use u. And we're replacing u with a function of f, with a function of f, with a function of x, and evaluate the integral that way, and then reverting back to our terms of x. So just as a quick example, the integral of 6x 3x squared plus 2 squared dx. Now obviously most of our integration using substitution won't be this easy, but we can see that our u term is going to be 3x squared plus 2. And du is the derivative times the differential dx. So the derivative of u is 6x, because the derivative of 3x squared is 6x, and the derivative of 2 is 0. Now we just need to add dx. And we substitute these terms into this expression, and we get the integral. So 6x dx is du, and we have 3x squared plus 2 is u. So we have u squared, 6x dx, du. And we have a simple integral. And we can just evaluate using our typical power rule for integration. And we have u cubed over 3 plus c. Now we just bring this back in, 3x squared plus 2 into u, and we get 3x squared plus 2 cubed over 3 plus c. And we can verify this. And as an exercise, you so wish, you can use the chain rule to evaluate this derivative, and you will end up getting back to the term that's inside of the integral. Another example. So now our example, so we have u is equal to x squared plus 5x. And then the derivative, the differential of u is the derivative of x squared plus 5x. The derivative of x squared is 2x. The derivative of 5x is 5. And then we add the differential term. So here we have 2x plus 5 dx is du over x squared plus 5x is u squared. Once again, another easy integral that we can just use this equation for. So we have u, so we can just rewrite this as u to the minus 2 du. So minus 2 plus 1 is u to the minus 1 divided by minus 2 plus 1 is minus 1 plus c is negative 1 over u. U is x squared plus 5x equals negative 1 over x squared plus 5x. Once again, you can evaluate the chain rule. You can use the chain rule to evaluate, and you will get back to this term. Now, we're not just limited to polynomial functions. And I'll show a very quick example of that right now. So let's say we want to find the integral of cosine of 2x dx. With the abilities that we have now, we can't do that, but we can use substitution, which is a very powerful method in simplifying this expression. So if we say that u is equal to 2x, du is equal to 2 dx. Here we notice that there aren't any 2's outside of the cosine. So we can algebraically manipulate our differential term to get du over 2 is equal to dx, and we can just substitute our terms for dx and 2x into the equation, into our integral, and we end up getting this equal to 1/2 cosine of u du. We can bring 1/2 outside of the integral and integrate cosine of u du. And we can remember from when we first learned the integration, the cosine, the integral of a cosine is sine. So we have 1/2 sine of u plus c is equal to u is 2x, sine of 2x over 2 plus c. And once again, we can check this using a chain rule, and this is a very quick check. So the derivative of sine of 2x is 2 cosine of x, cosine of 2x. 2 times cosine of 2x divided by 2 is cosine of 2x. Cosine of 2x is up here. And we can do this for exponents, we can do this for anything. Well, almost anything. Like if we had the integral of x squared sine of x squared. We can evaluate this, but we can't use it. We can't use substitution to evaluate that. Okay, so here's just a quick summary of integrals, and then we'll have one more example. So once again, we're just assuming that u is equal to f of x, and du is equal to f prime of x dx with these integrals. So the first, the integral of u of x to the n times u prime of x dx is equal to u of x to the n plus 1 over n plus 1 plus c. This is the one that we've already shown. 2. The integral of e to the u of x times u prime of x dx is equal to u e to the u of x plus c. 3. The integral of u prime of x dx over u of x is equal to the natural log of u of x plus c. So just as one more quick example, we're going to be showing a square root integral. So the integral of r times the square root of r squared plus 2 dr. Here we're changing the variables also, so that we're not confining just to x. So we're going to let u is equal to r squared plus 2. Du is equal to 2r dr. Once again, as we saw in our previous example, we don't have a 2. So we can write r dr is equal to du over 2, and we have r dr, and we have our u term, square root of u. So we can rewrite this as the integral. And I'm just going to skip a step. We're going to take the 1/2 outside of the integral. And we have the square root of u du equals 1/2 the integral of u to the 1/2 du. And that gives us 1/2 times 2/3 u to the 3/2 plus c. And we can just absorb 1/2 into the constant. And we get u to the 3/2 over 3 plus c. And we can just replace the u with the r squared. So we get r squared plus 2 to the 3/2 over 3 plus c. And if we plug this into this above expression, if we find the derivative of this by using the chain rule, we can get the term that is within the integral. And once again, as an exercise, if you wish to see how this works, I guess, you can evaluate all of these integrals, as well as checking your work, going backwards and determining what the derivative is of your end result to confirm that these answers are indeed correct. So thank you for coming back. I look forward to seeing you in our next video.